In this video, we're going to discuss the chemical potential and diffusive equilibrium. We're going to use exactly the same arguments that we just used with pressure in order to analyze a system that can trade number of particles back and forth between two systems. So in the bottom right, we can see we have a system containing two subsystems. So the left side of the system is part A, the right side of the system is part B. We will again assume that this system is in thermodynamic equilibrium, so the same temperature on both sides. And what we want to do is we want to allow the system to trade particles back and forth until it reaches an equilibrium state. And that is the state with the highest number of microstates and therefore the highest entropy. So just from a kind of logical point of view, we wouldn't want to put all of the particles on the right side in part B because there's just not nearly as many ways of rearranging the particles if they're all on one side of the box as if they are able to spread out throughout the entire box. So there must be some state that we can find in which the entropy is maximized. To do that, we simply take the partial derivative of the total entropy with respect to Na. Now, again, notice that this system, there's really only one independent variable in terms of the number of particles. If I define Nb, then Na is, by definition, defined, because Na plus Nb must equal the total number of particles. So if I know Na and I know the total number of particles, I know Nb. Okay, so taking the derivative with respect to Na, just picking one of the two variables here, the derivative of the total entropy must equal the derivative of entropy A with respect to Na plus the derivative of entropy B with respect to Na. We can now use exactly the same trick that we used in the pressure case to flip the sign of our entropy B derivative. So every time that the A side of the system loses a particle, the B side of the system gains that particle, and therefore we can say that the partial derivative of SB with respect to Na is equal to the negative of the partial derivative of SB with respect to NB. And this just means that we're taking the entropy of each side with respect to its own number of particles. The entropy of A is taken with respect to Na, and the derivative of the entropy B is taken with respect to NB. Again, we get to a situation where we find that these two derivatives must be equal to one another, which tells us that when A loses a particle, it loses the same amount of entropy that B gains when B gains that same particle, as they trade particles back and forth. And just like with pressure, we are going to call this derivative, which is maximized when the number of particles is in balance between the two systems, the chemical potential, which is equal to negative the temperature multiplied by the partial derivative of the entropy with respect to the number of particles, with U and V held fixed. So we're able to trade particles back and forth, but while we do it, we make sure that we hold the total energy and the total volume of the two systems constant. The minus T is really just a convention to make mu work better with the other variables like temperature and entropy, etc., as we will see when we talk about the thermodynamic potential. The chemical potential has units of energy because it is an entropy. The derivative of entropy with respect to the number of particles still has units of entropy, and entropy times temperature has units of energy. So the chemical potential has units of energy, and as we will see later, it actually can be rewritten in terms of a derivative of energy as well. Now that we've talked about the relationship between entropy and temperature, pressure, and the number of particles in the system, we can explicitly write the differential for ds. So if S is a function of un and v, we can write the differential ds as partial s partial u du plus partial s partial n dn plus partial s partial v dv.
where in each case we are taking the partial derivative while holding everything else constant. Noting what we have, well, this is just 1 over the temperature from our temperature video. This looks like mu over T, the chemical potential divided by the temperature, and this looks like the pressure divided by the temperature. So we can write ds as being equal to these 3 functions, though more commonly what we'll do is we'll actually write it in terms of du. So the infinitesimal change in energy as we change the entropy, volume, or number of particles is given by this expression here. And in general, what we're going to be doing is we're going to be holding 2 out of these 4 variables constant. So for example, if we choose u and v to be constant, the energy and the volume to be constant, then du and dv are 0. And this equation simplifies to 0 equals TdS plus mu dn. And then we can rewrite this in terms of derivatives as partial s, partial n, right? We're just solving this equation and turning our total derivatives into partials because we are holding the other variables constant. And we end up with negative mu over t, which is literally just solving this equation here. And we find mu equals negative t partial s partial n. And so this just gave us back what we just found as our function for the chemical potential mu in terms of s. But we can use this differential here in order to find a different equation for mu in terms of the energy u and the number of particles. So instead of holding u and v constant, we can instead hold entropy and volume constant, which means that ds is 0 and dv is 0. In this case, we get negative mu dn plus du, so we've just solved this equation with these two equal to 0, and we end up with the equation for mu as mu equals the partial derivative of n with s and v held constant. So these two expressions both give us an equation for the chemical potential, and it just depends on what variables we want to hold constant as we add particles to the system. In both cases, it tells us what happens when we add particles to the system. It's just what do we want to hold constant? Do we want to hold the entropy constant? Do we want to hold the energy constant? An example of a overly simplistic calculation of the chemical potential of a system using our new equation, where the chemical potential is the partial derivative of u with respect to n with s and v held constant. We're going to look at this kind of trial system of of a single Einstein solid, in 2 different states. So here is where we begin. We have 3 oscillators and 3 units of energy with an omega of 10. And just as a reminder, this equation here for the multiplicity of an Einstein solid comes from the number of ways of rearranging the number of units of energy and 1 minus the number of units of the number of particles in the object, where here the lines represent the separation between the particles and the dots represent the energy. So that's where this equation comes from, just as a reminder. Okay, so what happens is that if we keep the same amount of energy here as we add another unit of particle, our omega will actually increase, because now we'll have 3 units of energy to spread around more particles, so we'll have more microstates and therefore more entropy. So it wouldn't be S equals a constant. Our entropy wouldn't be constant if we left the energy the same when we add a new particle. So what we need to do is we need to remove a unit of energy. And this example is nice because we can remove exactly 1 unit of energy, and our multiplicity omega doesn't change, and therefore our S doesn't change. So since we removed one unit of energy, which we give by Q here, and since each Q carries an energy of E epsilon, remember this is just the difference between energy levels in a simple harmonic oscillator, we had to remove one unit of energy epsilon here, and so we have the change in energy per change in N is equal to negative of this energy, which is equal to our chemical potential, right? So in order to keep S constant, we had to remove energy. So actually kind of the more interesting thing here is thinking about what is the requirement that we need to meet in order to keep entropy constant as we add a new particle. In this case, we had to remove energy. In general, for most macroscopic systems at high temperatures, the chemical potential will be negative, because if we add a new particle, that will naturally want to increase the entropy, and in order to counteract that increase in entropy, we need to remove a little energy from the system.